and welcome to Mirabilis Design's webinar on faster alternate SystemC simulations. I'm your host Deepak Shankar and I'm the CEO of Mirabilis Design. I'll be taking you through an alternate solution that we at Mirabilis Design have developed that enables you to not only be able to get better simulation results but be able to do it extremely fast. Before we get started, there are a few logistics that I want to go over. You will be fully set in mute throughout the period of the session and the webinar. There is a control panel on the right-hand side of your GoToMeeting session. Within that, there's a chat window. You have the ability to type in any questions you have, and there are multiple people waiting in the queue for us to answer your questions. We have multiple application engineers waiting to answer your questions. Feel free to ask the questions at any time during the webinar. You don't have to wait until the very end. And there are people that will be answering those as soon as they are put forward. With this, I would like to welcome you once again to our webinar, and we're ready to get started. A quick introduction to why we have this webinar. Mirabilis Design has been doing webinars about at the average of about one every 2 to 3 weeks. This webinar is a little unique because we're really talking about how a solution we have, which has been proven in over 50 semiconductor companies, really provides you an extremely high performance and fast modeling solution for system design. One of the things is that it takes away this characteristic that everybody goes after, which is a code based, and is really focusing on more of a graphical based approach. Now during this webinar, I'm going to really show you the difference between the two types of modeling, but also highlight why you're able to get the extremely high performance in terms of model construction, simulation, model capacity, and also the depth of analysis. Along the way, I'm also going to share with you some of the libraries that we have and also show you some of the examples of usage that we have done with our environment, or some of our customers have done with our environment. A quick introduction to Mirabilis Design. We're a provider of electronic system level tools that has probably the largest collection of IP blocks that allow you to very quickly assemble up the systems. Our innovative technology, VisualSim, is really being used all over the world for doing a variety of power and performance related analysis, anything from hardware software partitioning to energy conservation to looking at reducing the read-write latencies to increasing the battery life. In addition to our standard VisualSim technology, we also provide customized platforms for specific customers that they can use either internally or with their customers and suppliers as well. We are based in Silicon Valley, and we have a large collection of experts in system modeling and architecture exploration. Now, VisualSim technology is a completely graphical and hierarchical modeling environment. The hierarchical is important in the sense that it allows you to very easily capture and store sub-components, sub-elements in your system that can be shared across other members of your organization. With the VisualSim technology, you can actually model your hardware, your software, real-time operating systems, interfaces, and everything else that goes around it, including the analysis tools, traffic, and networks, things, and also use cases. Typical application of VisualSim tends to be architecture exploration, power analysis, which can include anything from energy harvesting, analysis, management, and consumption. And of course, you got the performance analysis and hardware software partitioning as well as capabilities that are used from the VisualSim environment. Now, why did we start up on VisualSim? One of the things that we have seen over time is a lot of challenges with code-based development. It's not so much that code-based development is bad, it's just that when you want to use it for long term, the challenges really start surmounting and it becomes very hard for a number of organizations to keep up. First and foremost, it's very hard to create ready-to-use libraries that don't have, have to conform to specific protocols or specific data types, which means it becomes very hard to just simply, plug and play two components very quickly and very easily. The other one is code maintainability, which is, when some of the staff change roles and another staff takes over, there's a huge amount of effort in terms of ramping up and getting used to the fact that you can, need to modify the code or need to do maintenance in the code when, say, for example, your simulator moves from one generation to another. The other aspect is the inability to very easily mix and match different types of simulation models. So it can be like, I want to mix analog and digital, or loosely timed and cycle accurate. The inability to do all of those easily and very quickly. Now, what are the major advantages of going with the graphical approach? First and foremost is from day one when you start assembling, you can quickly visualize where you're going to end up. You can create these empty shells and then start adding data to each one so you can see what your final system is and how you're progressing. The other part is presentation. One of the biggest important features of systems engineering or system design is the ability to be able to communicate your design to everybody involved, be it your marketing organization, your end customers, or your suppliers. The other part of systems engineering is to get everybody involved, and graphical simulation allows non-modelers, non-programmers to be able to just see, oh yeah, here's what my real system is going to look like. I can very quickly do my system design and analysis. Now, another advantage of graphical environment is the ability to create folders and libraries where you can have ready-to-go components that for the next person using it can very quickly assemble their system. Another major advantage is not worrying about Linux or not worrying about migrating from a Windows platform to a Linux platform, having to compile each time I make a change. All of those requirements go away in a graphical environment. Now, first what I would like to do is quickly just walk you through the VisualSim environment. So this is the VisualSim architect environment. As you can see, there's a series of libraries on the left-hand side. The block diagram editor here is where you construct up the model. You can see you have things like traffic generators that are more stochastic, but then you have things like your AXI buses or network on chip or PCI Express, things like that, that you can set up using these parameters. And then, of course, you have like memory controllers and DRAMs. In addition to that, you also have some of the setup, like for example, the parameters that you can configure and keep changing to try different experiments. You have utilities like the power manager. Now, once I assemble up a system using the libraries on the left-hand side, I can go ahead and click on the Go button, and I can go ahead and run a simulation. Now, what I'm focusing on right over here are two aspects of my design. The first aspect is the first aspect is the fact of combining the timing, which in this case you can see the activate and the writes and the refreshes, with the power consumption. So the red line over here shows me what my average power is, which is typically what you compute when you do your analytical or Excel-based model. This power blocks over here really show you what the instantaneous power becomes important when you're really thinking about what is my thermal map, looking at aspects such as what should be my insulation, what's going to be my cooling, attributes like those. In addition to that, you also get textual reports here, like for example, this is a report on one of the memory controllers. You can see over here, and there's actually one right back there. Another aspect is you can also get more of a battery view. So if you're doing a mobile device, you can also see what your battery availability is. So what it means is that you can build a system using the basic building blocks. You can get a variety of these predefined reports, and you can assemble up these systems very quickly in a matter, sometimes in a matter of a day or so, and you have your systems up and running. Now, going back to the presentation, some of the major graphical modeling features in VisualSim are really split into three parts. The first one is the ability for you to very quickly construct models, share models, and analyze. So one of the key advantages that you have in VisualSim is that timing, power, and functionality are fully integrated. So for example, if you look at the same model again and look at the memory controller, it has all the timing information, but at the same time it has a logic associated with the LPDDR, for example, here, or the command buffer, or the logic associated with the addressing, or the arbitration. In this case, we're using the default arbitration. It also has information on your power. So it's got the timing, it's got the power, and it's got the functionality in terms of arbitration and control, all built into the same library block. So there's no need for you to go to multiple environments to be able to do your analysis. Now, the other aspect is all the utilities. So one of the things that we have as an advantage, and I'm going to move back into the environment here, I'm going to open up a new window. The purpose for doing that is just want to construct a simple model to kind of highlight to you what it takes to build a system. So I'm going to bring in a simulator to specify how long I want to run it. So I'm going to say I'm going to run it for like say 5 milliseconds. It should be fairly fast. And then I'm going to bring in a traffic generator to trigger the system. I'm going to bring in say, let's bring in an ARM processor right now. So I'll bring in an ARM processor right there. I'm going to bring in all the software details related to the ARM, including the operating system, the software tasks, and all of those. I'm going to, I don't need the traffic generator here for now. And then what I'm going to do is I'm going to bring, say, for example, let's bring an AXI bus into the mix. So I can put in an AXI bus over here. I'm going to connect this up here. And then I'm going to bring, say, a memory module. In addition to that, I can bring some of the peripherals right into the place. So for example, I can bring a, let's bring in a PCI Express, which actually can connect to an external world. And in between that, I can bring in a bridge. So what I've done is I've actually assembled up A9 Cortex along with all the traffic and the software with an AXI bus, DRAM, bridges, and a PCI Express. So essentially put together a simple model. Now what I'm going to do is I'm going to go ahead and run a simulation. What's going to do is it's going to immediately highlight to me all the different errors. So for example, it says that an architecture information is not available. So I'm going to go ahead and add that. This is the one that maintains all my statistics and all my data information. Now I'm going to rerun it. So every time I run it, it actually captures all the different errors that are in the model. So that way what I can do is I can actually keep adding them or correcting them as I go along. So here's another one where some of the software profile data is missing. So as I go along, I can keep making corrections and building it up. I'm no longer worrying about code. I'm worrying now about how my system is operating. So this is a major advantage of using a graphical environment like this. Now just to remind you again, we do have people standing by to answer any of your questions, so feel free to type in any questions that you might have on the chat window. Another aspect which I just showed you right now is all these different reports and analysis tools and things like that that are already pre-available. The other aspect is the model debugging. You're not debugging code here in this case. You're really debugging how your system is operating, how your system is behaving. So you can actually use a lot of the GUI features to communicate between blocks within the model and also aggregate statistics all in a remote location, so you don't need to have it all tied into the blocks themselves. Because of the hierarchical nature, you can actually manage your modules and subcomponents. So if I go back to the model we were looking at here and I go into this Cortex-9, I can click on it, I can see what's right inside. You can actually notice a dual arm cortex. So you do have the ability to manage these in a hierarchy. And one of the things you notice when I run my mouse over, tells me where it's located. One of the key things is this doesn't have to be located locally. It actually can be located in some remote locations. More of that a little later when I talk about it. Now, before we go into too much details of the modeling at the graphical level, talk a little bit about the legacy. So you do have the ability to import code, import your RTO or import your SystemC modules. Plus, you also have the ability to import algorithms that might be written in MATLAB or Python into the model itself. And once they import it, they just behave like just another building block in the environment. Certain restrictions are there in that we assume it's compiled code and it's fully verified code. Now, once you integrate it, it just becomes part of the library, and you have access to it for all times. One of the key things in VisualSim is the ability to mix analog and digital within the same modeling environment. So I'm actually going to go. There we go. Oops, sorry. There we go. So in this case, the top level, the stuff that we see over here are your processing, the processor on the digital side, and right inside of here is the analog component in your control. You can see it's actually a second order system with 0 holes and transfer functions and things like that. So when I go ahead and run the simulation of this, which combines digital and analog, you can actually see the damping circuitry, but at the same time, you can also see how the digital side of the system is behaved. You know, what's the buffer occupancy, what was the latency across the system, and things like that. So you do have the ability to mix and match digital and analog within the same environment. Now, why are the pre-built library blocks critical? So one of the things about the pre-built library blocks is that they've been done with a set of intelligence that allows you to take these blocks and customize it for your particular implementation. Typically, if you get some code from someone and you have to customize it, you have to rewrite the code. But in the case of VisualSim, that is not how the system behaves. The way the system behaves is that you have, say, a building block like this, which is all about a battery. Let me bring up a building block. Okay, here we go. So this is the power manager block. It has a unique set of parameters. So by defining the value of these parameters, you can construct up your particular implementation. So now if I take, say, another model, the model that we were looking at a little bit earlier, not looking at a little bit earlier. Now when I double click on the axis bus, you'll see it's got something like about 25 parameters. The reason it has so many parameters is because there are so many variations in the market. With these parameters, you have the ability to customize it for your particular implementation. Anything from completely modifying the arbitration to having like a single request versus a multi-request dual channel, to things like, what's the buffering, what's the read-write thresholds, of course, standard things like the clock speeds and the bus widths and things like that as well. So using this, you can customize it for any sort of implementation. So the selection of the parameters is actually a very critical part of the way VisualSim has been set up. in that the parameters have been set up such that it ensures that 99% of all the users can quickly create their own variation of that particular implementation. Now, another aspect of VisualSim is the ability where you can actually scale to very large systems. So here, if you notice, we have one of these hierarchical blocks over here, which was one of those dual cores. The question comes up is, how do I scale this to where I want to put a system that has a large number of these? So in this case, you have something like about 12 of these processor modules, and each one has their own completely independent traffic that feeds into a PCI Express that has a backbone of these memories. Of course, at top level, you have all these parameters. So what this allows you to do is take those blocks you created as hierarchical, put them into your user library, and then instantiate them multiple times within your system. To give you an idea of how that works, say I go into this one over here, and I have this particular component. So what I'm going to do is I'm just going to put that right over here. And what I'm going to do is I'm going to take this and say save block in library. So once I put that right in here, and I go ahead and save it, now when I go open my user library over here, you can see my ARM subsystem is over here. So now I have the ability to just drag and drop it over, and now I have that particular block that can be instantiated multiple times in my particular implementation. So with this, I can create very large systems just by instantiating each one of these. Do it very quickly. Now, another aspect of VisualSim, which we actually looked at it lightly but didn't go into much detail, is that you do have the ability to do a power versus timing trade-off. So one of the things that challenge that many people face is that you have a separate model for timing and a separate model for power for your power consumption. In VisualSim, they get integrated into one and the same. So what does that mean? What it means is that, I can actually see, I have my activates, but at the same time, I have my writes and my refreshes, and I can see associated with that, how much is the peak power consumption. So I got my red line, which is my average. I can look at these to tell me what my peak power consumption is. So how does this really help? It helps me visualize what is causing these higher power consumption. Also helps me visualize how I can modify the behavior of some of this execution. That way I can, for example, this section over here, how can I reduce the power consumption in those systems? So it gives me an increased amount of visibility into what my system is doing. So to give you an idea of how that works, I'm just going to open up a model. So this is a model that we have here, and actually one of the things about this model is that the model is not local. So let me just bring up something that's a local model on my desktop. Here we go. Okay. Now what I'm going to do is, now that I have a model already set up, I'm just going to go ahead and run a simulation. I'm running the simulation for about 20 milliseconds, and you're going to notice it takes about 20 to 22 seconds to run about 20 milliseconds of the entire chip. This is an entire SoC that we're looking at simulating right now. What I want to do is, in this model, is I want to look at modifying the architecture such that I can get about 13,000 frames processed within that 20 milliseconds, while at the same time keeping the power consumption below 1 watt of power. So this is the power, and when I look at it, you'll see that I get about, actually I'm less than 1 watt of power. But then when I look at the performance, which is this video frames per second or per unit time over here, so 10 to the power 3, I get about 6,600 as my peak. I really need to be at 13,000. So now using some of the other statistics we generate, I figure that I can move this rotate frame to hardware accelerator. So rather than having to recompile, set it up differently, I just go ahead and make this change here to say go from software to hardware. I'm going to go ahead and rerun the exact same simulation. Now, one of the things you'll notice right up front is you can see the hardware engines and see when are the periods that it's busy. Plus the other thing is I also get visibility into what is the power consumption. Now, one of the things adding the hardware accelerators caused is to shoot up my power consumption to about 1.5 milliwatts. So I still have this, which is a sub 1 watt, but as my execution increases and more processing happens, it actually bumps it up to 1.5 watts of power. Now let's look at the performance. So this is power 10 to the 4. I get about 14,700. So I'm actually able, actually 14,750. I'm actually able to now meet my performance goals, though I'm not able to meet my power goals. One of the things that I was mentioning in VisualSim is you have the ability now to not just handle the power, handle the performance and the behavior, but also handle the power. So in this case, what I'm going to do is take this hardware accelerator and I'm going to enable power gating for it. Now, in this model, we're doing a very crude form of power gating, which is as soon as the processing is completed, it just drops down to a standby mode. We'll rerun it. Again, it's running for 20 milliseconds right here. And I'm going to go ahead and try to see how it's performing. Again, focusing on the same two attributes. One is the power and the other is my frame performance. One of the things that you can see right up front here is that the power has dropped back to below 1 watt of power. You can see here it's pretty much just dropping as soon as it's completed. Unfortunately, the performance has also dropped. We're getting a peak performance of about 13,350. We were at 14,650. We dropped down to 13,350. So it's a drop of about 12 to 13%. So to get my power down by this amount, I actually have to take a 12 to 13% hit in my performance. So that's an aspect that kind of introduces some additional considerations for me, because the positive thing is I'm able to get it over the 13,000 mark, but then I want to see if it's like too close to margin, what else can I do to get the performance. Now, to be able to visualize that, we also provide you textual statistics. So for example, here I can see the utilization of my flash, my DRAM, also look at the processor pipeline, look at the the utilization of the different subcomponents within my system, and then I can also get visibility into what was my. I'm going to go here to look at my DRAM throughput. Look at what was the IOs per second on the bus. Go up a little bit here. Oh, here we go. That's my SDRAM throughput. What is my what was my input and output buffering? So one of the things you're going to notice is I've got a significant amount of a peak time. I've got about 8 words that are being backed up on the DRAM, which means they're being buffered on the DRAM. This tells me that potentially the memory controller buffer could be extending, so you might have a higher amount of queuing delays. Now, if you go back and look at the cache and get a feel for what is the stall time, you can see I'm already getting about a 1% stall. Not significant, but I'm getting a stall of 1%. And if I look at my iCache, I'm getting about a 78% hit. So what this tells me is that I'm actually getting a fairly good amount of application hit right inside the iCache. So I don't really need to keep prefetching and have misses that go out to the DRAM. So my system is actually working fairly efficiently. Again, these are statistics that are automatically generated by VisualSim without you having to go recreate them. So these are already predefined components that we have in our library. Going back to the presentation, you can actually create your own customized reports as well. In this case, one of the things that I have is over time, I'm looking at what the MIPS performances of my processor cores. So these are my different cores, and I can see the peak performance here is about 147 MIPS, where the lowest performance over here is about 137 MIPS. So I can actually create these kind of custom plots or statistics as well as part of my design or as part of my model effort. Now, one of the things that we have in VisualSim is the ability to mix and match statistical and cycle accurate and functional all within the same model. So in this case, as you can see, the traffic generators that resemble the masters are all statistics, essentially a traffic generator. But then the AXI and the memory controller and the hardware DRAM, as you can see the parameters over here, are all cycle accurate. They're also functionally accurate. So I can very easily mix and match both of them and not have to worry about data types, not worry about conversions, nothing. Just plug them together and I have a system that's ready to run. So this allows me to be able to put very, very complex systems together in a very short period of time. I don't need to have all the data. So for example, over here, I don't have all the data yet about my processor because I haven't selected. I'm only interested in the backbone. I just put a traffic generator as opposed to bringing in a real processor model to run through the entire system. Now, one of the things in VisualSim that makes it very unique is that you can actually integrate a lot of the functional details you might do in hardware and software. So for example, you can do more of the standard ones like the width, the clock speed, the buffer depth, the queue algorithms, the arbitrations, things like that. But what you can also do is you can integrate addresses and combine data and control. Plus, you can handle some of the signaling and handshaking as well. So one of the things we're going to do is go back to the environment. There you go. And what I'm going to do is I'm going to turn on some of the debugging information that is available within the environment. So I'm just going to turn on some of the debugging. And what I'm going to do is I'm going to actually add I'm also going to turn on debugging on the memory itself, not just on the memory controller. So you can see I'm just making the changes on these things. Notice again, I didn't actually have to do anything special in terms of configuring the interfaces or things like that. I was just reconnecting them and they're ready to go. I think I got all of them. Yeah, I did. So I'm going to go ahead and rerun the exact same simulation, but now what I'm doing is I've got these statistics that I'm generating. So once I've run it for a little while, I'm going to go ahead and stop the simulation. And what I'm going to do is I'm going to take a look at what is being generated in terms of debugging. So for example, right up front, you can see I got a write start that was going to bank 1 with an address, row, column, and bytes. And you can see right here the RAS was started at this time. There's an RRB, so they row to row for a bank. And then there's a RAS complete, RP start, RP complete, RCD start complete, and then my write sequential takes over. So one of the things you have the ability to do is you can not only combine your addressing, but you can also combine your signaling into the same model. Now, how are these defined in the model? The way they're defined in the model is in a combination of parameters. So for example, over here, I specify where my column, rows, and banks are in the address field of the transaction coming in. Now, right up here, I can create a variation of these addresses. So I use logic here to create which address I'm interested in looking at. So with that, I can actually combine my address. The model already has the signaling, plus I have the stochastic portion, and then I can configure this to make it look exactly like my behavior. So you have now an environment with all these IP libraries, and you also have all the building blocks that allow you to very quickly assemble up these systems. Now, before I go into too much detail on the libraries, I'm just going to give you two high-level views of the libraries. There are two types of libraries. The first one is statistical modeling libraries. So rather than having to worry about the exact configuration of an access bus or DRAM, I can describe each of these building blocks as a combination of a traffic, a queue block, a resource, power, and reports. And then I can run a variety of simulations to very quickly, I'm talking about in hours, be able to visualize how my old system works. So for example, moving back into the tool, I'm going to actually bring up a model here that is a heterogeneous multi-core architecture. So 3 modules, each of them has variable number of cores, and they actually have different clock speeds as well. And they all have L2s that are connected to an external L3, goes to a crossbar to memory controllers, which has 4 DRAMs, IOs, PCI Express, Ethernet interface. And then I have my behavior right over here. When I look into my behavior itself, you can see it's the behavior of my application that is displayed in the behavior over here, which is what is the sequence that the application follows. And then, of course, the dispatcher to say which core I'm going to be sending it to. Now, what I'm going to do is I'm just going to go ahead and run the simulation. Now, one of the things that you're going to notice, which is very interesting over here, I've got a statistical model. But you can see all my cores, my L1s, the L2s, the L3s, the DDRs, all of those get plotted in timing diagram mode here. So even though I'm using statistical blocks, I still have the ability to create cycle accurate views using those statistical blocks. So for example, if I go into this and I look into the processor core and I open it, all I really have for the block is what's called a scheduler, or a system resource. So, it has a scheduling algorithm, it has, the buffers, it has the clock speed, the context switching time, all of that information. And you have the ability to, use that to describe one of the processor cores and still be able to get cycle accuracy. This is actually one of the advantages of VisualSim, is where you only want to go down to cycle accuracy because obviously you're going to take a performance hit. Only go down when you need that level of information. You don't need that level of information. You can be at a statistical level, still get cycle accurate details. Now, another aspect is the cycle accurate modeling. Now, of course, once you get into more detail, you would want to actually model the hardware details of the system. So that's where you drag in and block maybe a network on chip, or a DRAM, or a PCI Express, or a software block, or a processor, and then you assemble up the system, and that's where you start getting timing diagram details. You look at the bank level, you look at signal level, you look at detailed statistics. So for example, when I go back to this model and I rerun it, stop it. If I just zoom in to say one small region over here, I'm going to go between 2.2 and 2.4, which is 22 and 24 microseconds. What you're going to be able to see is these are related to the 8 banks of my system. So there's write activity related to the 8, and then there's the activate pre-charge related to the banks themselves. Now, associated with that, you can see what the power consumptions are. So this is going to tell you, for example, right here, I want to understand why I have these blue dots right over here, which are causing these peaks. Because if I have those, now what that's going to happen is it's going to cause me to have to plan my heat insulation, my cooling for this level, not at this level, which is where the whole overall power statistics is. So at this point, what I'm looking for is, are my signaling correct? Are my addresses correct? I'm looking at clock by clock, what is happening in terms of behavior of the system. You would use the cycle accurate building blocks that we provide. Now, this one here is a series of libraries that we provide for the semiconductor level. Now, we also have libraries at the system level, which is an add-on to this library. But then, as you can see, we've got a huge library of modeling components at the semiconductor level. Processors themselves, we've got over 100 processors that we have modeled, a whole variety of them. And so we have those also predefined and available in the library as well. Now, one of the key things of VisualSim is that we're completely graphical, but when it comes to actually running a large number of simulations, we don't expect you to be doing it right from the GUI, especially when you're running hundreds. Rather, we provide you a command line which you can use Tickle or Python to be able to distribute your simulations across cores within a single processor or a whole farm of servers. One of the key things we've done is you can actually take simulations and send them across to individual cores, and you actually have no degradation in performance, assuming you have a good amount of memory. You have no degradation in performance. So, for example, if you have a 4-core architecture, you can send 4 simulations to run concurrently, and you'll get the exact same performance you were seeing earlier. The other thing is on the return path, we do have a post-processor that's a single viewer to combine simulation results from multiple simulations. Now, one of the things that we pride ourselves based on working with over 50 semiconductor companies and over 200 projects, we found that we are the fastest system-level simulator in the market today. And one of the things that makes us very unique is we can have extremely large model capacity. So, for example, we have had models of PowerPC and ARM-based system where there are like over 200 to 250 cores that are part of a single simulation model, and you can still get results within a reasonable amount of time. So that allows us to create extremely large models with an accurate amount of detail that you can get within the simulation. Now, one of the aspects of VisualSim is the ability to share. Now, it's not just about taking these library blocks and making it available in a different environment. Rather, it's the ability for remote teams to work together where the library components are located remotely, but then the model can just reference those remote library locations, and you can have a fully constructed system. When there are changes made remotely, those are immediately reflected in the model. Another aspect is that you don't have to worry about paths and block locations and things like that. Whether I'm running Windows, whether I'm running Linux, whether I'm going to Mac, doesn't matter. It just seamlessly runs across all the platforms without you having to make any changes underlying. Another aspect of VisualSim is the ability for you to view, modify, and simulate directly from a web browser. Why is that important? What it allows you to do is, for example, over here, I've got my documentation which has been set up on this page here, has the block diagram, shows the VisualSim model, discusses all the configurations, shows some of the plots and results and things like that. Now, on the same page, I actually have, so notice here, it says mirabilisdesign.com. So this is actually being scheduled from our server in Florida. So you opened up this model from within a web browser or within a web page. Now, when I go ahead and run the simulation from here, I can actually run it at the same speed that I would be running it if I was on my desktop. So what does this provide? The ability for you to be able to share your models across your ecosystem, be it your customers, be it your suppliers, your marketing organizations. Anybody can come in and say, let me try to analyze certain components. So for example, I want to increase the clock speed of, say, the bus. Can I still maintain my end-to-end latency, or is there going to be a buffer buildup? Or for example, your solutions architecture team can look at it and decide, how do I promote this for a particular application? What if I try this out for, say, a networking router? How will be the behavior of some of these things? So it allows me to be able to present this right from within a web browser, which means even if I'm in a remote location, I can log in and be able to access these models. So it allows for a great amount of sharing within your ecosystem. So in conclusion, VisualSim just provides you all the ability you have with code-based, but it provides you the ability of greater visualization and the ability to very quickly assemble models using predefined building blocks that we provide you, or blocks that you might have from your legacy system. With this, I conclude my webinar presentation. We're now open for any questions. Feel free to enter those questions in your chat window, and there are people standing by to answer some questions. I believe there are already been a number of questions that people have asked, but feel free to ask any additional questions as well. If there are no more questions, I thank you for attending this webinar. You will be getting a copy of the slides and a link to the webinar in a day or so, and our application engineers will be contacting you to answer any additional questions. Thank you very much and have a wonderful day.